Hello everybody, and welcome to my new channel. Today we'll start building a historic style computer made exclusively from discrete components. While our computer will functionally be closer to a more modern 8-bit computer with a 16-bit address bus, so that we can actually do something with it, the technology employed will mimic the ones used in 1959's IBM 1401. It'll be diode transistor logic, or commonly known as DTL. I will, however, cheat a little bit with the memory since I'm not patient enough to weave thousands of little iron cores on a net of copper wires to get the back in the day commonly used core memory. I'll just use a modern memory IC for that, so those will be the only ICs that I will use in the project, though. So, why do you think anybody would be interested in even building a computer that is most likely won't run any faster than a couple kilohertz? Well, it's more for replicating history than usefulness, and yeah, well, it's fun designing a totally new computer with your totally own instruction set, and yeah, see how people back then did it and how that stuff works and what we can do to optimize it as much as we can without leaving the historic setting that we are in. So at this point, I want to mention Ben Eder's channel really quick, since my computer design is moderately to heavily based on his breadboard computer. Um, his is a great channel explaining how computers works. However, he does use TTL logic ICs for his computer, and well, I want to do it completely discrete. So, thanks to Ben Eder for inspiring me, and yeah, let's have a look at that. I'll put a link to his project down in the description below. So first, before we start with anything else, let's talk a little bit about the history of computing. So the history of computing started back in the days with, as you can see here, the Antikythera mechanism. Hope I pronounced that correctly. And it used to be like mechanical computers back then. The mechanism here had 37 bronze gears, which enabled the user to calculate the positions of the stars, the moon, and the sun across the skies during the year. So basically, they were able to predict the movements of celestial objects with that, which was immensely helpful for navigation and yeah, seafaring back in the days. That's also why this piece of history was found in an old shipwreck. Analog computers aren't totally historic, though. I mean, there are very or relatively modern examples of analog computer up to and including World War II and later. So in World War II, the US Navy Mark I fire control computer, which was used to calculate ballistic trajectories and factored in things like wind, elevation, and basically everything you could imagine was a mechanical computer. Basically, you dialed in where you wanted to have your round targeted, and the computer basically calculated which azimuth your cannon would have to be at to hit that target. It was pretty precise. However, we don't really want to build an analog computer, so let's go on a little bit further, which to something that resembles our modern computers a little bit more. So what you see here on the left is what some people might say is the first, in quotations, computer. It's actually not a real computer. It's a tabulation machine, the IBM 100 punch card tabulator. And what this machine did is you fed it with punch cards, which are basically paper or cardboard sheets that have holes punched in at certain locations, and that machine read those punch cards and, as the name already said, tabulated the results of those. So it basically counted how many times one hole was punched and how many times another hole was punched. Yeah, that was extremely valuable back in the days, especially for the census in the United States, which was the first official thing that such a tabulating machine was used. Yeah, those machines later got some more features like addition, subtraction, and other things that made tabulating easy. They weren't a completely free programmable machine, though. Let's look a little bit forward into the 20th century here, though. So, for much of the early 20th century, computers were thought of by people, or as people who actually did calculations. So, they were personnel that did nothing other than calculate stuff for engineers. And they sometimes used mechanical computers to help in their additions, subtractions, divisions, calculating of differential equations, etc., etc. But yeah, they were people, and you might know from the movie Hidden Figures, a perfect example for this, Dorothy Vaughan, who was one of the first black section chiefs at NASA in a time where segregation and racism unfortunately were rampant here in the United States. And yeah, that basically helped bring NASA more to a modern age where they respect all people regardless of the color of their skin. And yeah, she basically also learned, once NASA got their first actual electronic computer, how to program that, and became one of the leading Fortran programmers in all of NASA up to 1971. So let's have a look at actual computers, or at least what we today might think of computer. So let's start a little bit with theory here. You might have heard the name Alan Turing. He was one of the most brilliant British computer scientists. He was integral in the development of Colossus, which was a giant analog computer that allowed the Brits to decipher the German Enigma encryption back in World War II. However, before that, actually, in 1936, Turing published a paper which was called On Computable Numbers, with an application to the Entscheidungsproblem. So the Entscheidungsproblem was formulated 8 years earlier by German Wilhelm Ackermann and was a challenge to prove calculability. So basically, proof that you could calculate something. Turing found, independently of Alonzo Church, albeit with different methods. So Alonzo Church used something like lambda calculus, while Turing used a Gedanken experiment that we'll talk about in a second, that proved that certain machines can basically calculate everything that is calculable, which obviously is a big simplification, but that's what they did. And I won't go any deeper in that. There is material available at other places for that. And yeah, such machines became known as Turing complete machines. So basically, if you have a computer that can calculate everything that is calculable, it is Turing complete. And for a very simplified way to say that is, you need addition, subtraction, and the capability to perform all basic logic operations, as well as jump operations and conditional jumps. at least technically you need conditional jumps. There are some exceptions to that, which we'll talk about in just a second. So that first exception, which actually was the first fully Turing-capable computer, was an electromechanical relay computer, the SUSE Z3, which was developed by German computer scientist Konrad Zuse. And this machine actually did not have conditional jumps in it, so therefore its Turing completeness has been questioned until 1998, actually, which is more than 50 years after it was built. At that time, Professor R. Rojas proved that if you structured your programs in a way that all the loops that the computer could possibly take are basically read out in the or written out in the program and expanded, then it would be a Turing complete machine. Practically, that is not possible, but theoretically, yes, the SUSE Z3 is the first Turing capable computer that was developed in the world. Let's see what a little bit later happened though. So on the left here, which is the first fully electronic computer built with 18,000 vacuum tubes that were used as logical switches, is the ENIAC. It was completed by the end of 1945 and was primarily used to calculate firing tables for artillery, which, as you might remember, previously was done with a mechanical computer, and was also used to study the feasibility of thermonuclear weapons for the Manhattan Project in the United States. As said before, 18,000 vacuum tubes, and I mean, a vacuum tube is very similar to a light bulb. So you can imagine that, at least if you lived in a time where we still had incandescent bulbs, that those bulbs actually burned out quite a bit, and people were employed more to fix the computer than to do actual calculations. So that first fully electronic computer was a maintenance nightmare, but it worked when it worked. On the right here, we can see the actual first widely used computer, which is the IBM 1401. That one was introduced in the late 1959, and it was a transistor computer, so it didn't include valves anymore. It included over 10,000 discrete transistors and used them in a diode transistor logic setup. Ran at a clock frequency of a whopping 86,957 hertz, which is just about 87 kilohertz. Imagine today our computers run at multiple gigahertz, which is multiple orders of magnitude faster than that. But back in the days, the 1401 was the first mass-produced computer. It came with a whopping set of accessories, plotters, printers, punch card readers, tape drives, etc. And if you watch movies that either play in those old days or have any computing background in them, you might often see those big tape drives in the back that spin like crazy from left to right. And yeah, those were used for those IBM 1401 computers back in the days. And yeah, I mean, technology-wise, the computer that we'll be building will be similar to the 1401. However, obviously, it'll more resemble a reduced instruction set computer or microcontroller that we know from today. And it definitely won't have all of the accessories that the IBM had, even though we could probably set up an interface to most of them. But yeah, we are not going to do that. You can do that if you want later, but for me, I'm probably going to stick either with just a parallel or serial interface eventually. and see how much performance we can squeeze out of that machine. Okay. Well, that's it, everybody. Thanks for listening, and please subscribe and like this video if you do like it. It helps a lot. And I will see you in the next episode, where we're basically gonna go a little bit over theory of logic circuits. And after that, we'll have a look at those circuits on a breadboard. So see you then.